Hello, my name is Pak Poon and I currently have a Bachelor of Science in Mechanical Engineering. I redesigned the previous year's sub design from a two-in-one back into its respective group, frame, and hull. The competition wanted an autonomous underwater vehicle (AUV) that is submergible, waterproof, buoyancy positive, and can fit within certain weight and size requirements. The redesign was due in part to a global pandemic and meant manufacturing was going to be difficult. During the beginning of the year, it was unsure if the competition were going to happen, and in the chance it was going to be an in-person competition, then I would have to make the assembly of the sub easier, and that would mean giving up the original unique idea, which would have required sophisticated machining, and instead opted to have parts that can be easily put together with hand tools. The frame is mostly created from anodized aluminum T-slots that's 1 inch by 1 inch, connected with M3 nuts and screws. The hull is purchased from Blue Robotics along with the propulsion systems and mounting brackets, all connected with M3 nuts and screws, with any missing brackets created from 3D printed ABS filament. The housing of the electronic component is done with a hull purchased from Blue Robotics. A custom 3D printed electronic plate had to be created to place all the electronics on. An external battery housing is created also to store the battery and to have easy access without entering the main hull. The mass of the AUV is approximately 36.82 pounds, just the sub without any attachments such as claw or dropper. The length of the sub is 2.66 feet, the width of the sub is 2.04 feet from propeller to propeller, the height of the sub is 1.34 feet from the bottom to the propeller. Based on hand calculations, the buoyancy that is given from the hull and battery housing is going to be approximately 32.48 pounds. The submergibility of the sub is met by using the double O-ring configuration from Blue Robotics, and testing would have been done by going to a pool and physically submerging it without electronics first to ensure the seals were working properly.
Hello, my name is Christopher Riza-Nakonechny. I hold a Bachelor's of Science degree in Mechanical Engineering from California State University, Los Angeles. The functional requirements of the hull include the need for the AUV to be submergible and house electronic subsystems. This means in the performance requirements is that the hull must be 100% waterproof up to the operational depth of 5 meters for the duration of the allotted time, 20 minutes. In engineering, meeting a requirement means exceeding it by a reasonable cushion called the factor of safety. And the requirements also include the need for a minimum of 0.5% positive buoyancy upon shutting the AUV down through the kill switch. Lantern's design met the requirements of housing electronic shelving most efficiently with its cuboidal shape. Its profile matched the electronic shelving profile. The flat walls also provided ease of cutting and attaching components. Examples include the two hemispherical windows for cameras and the port junction connecting cables from the inside electrical components to the outside of the hull. Lantern's design met the requirements of submergibility by welding the joints. Stress tests were simulated using SOLIDWORKS finite element analysis capabilities. Each of the attached components would require waterproofing in itself. The circular windows for the two cameras would require simple O-rings. The square plate holding the port junction would be welded on. The most difficult waterproofing location was the lid. Our design used latches to secure the lid onto the hull with a securing force, but the mechanism of waterproofing was yet to be determined. Meeting the 5-meter depth. According to the stress analysis, it was determined that the inherited design did not provide enough strength to manage the stress at 5 meters with a high enough factor of safety. During the competition, there was little cause for concern of external stressors, but the initial design found weak points with only a factor of safety of 1.1, which does not provide confidence. These tests were done with a weld bead side of 0.21 inches integrated onto the test using SOLIDWORKS available tools. The highest stress was located at the lip, designed to attach to the acrylic lid. Considering longevity for future teams, robustness against wear and tear, and the fundamental importance of maintaining the integrity of the waterproofing of the electronics, at least a factor of safety of 2.5 was determined acceptable. 3 modifications were made to the inherited design. The thickness of the 5 aluminum walls was increased from 1/8 inch to 3/8 inch thickness. Alone, this modification increased the factor of safety from 1.1 to 1.3. The second modification was to increase the extended lip by 0.2 inches, increasing the factor of safety to 1.9, taken in isolation. The third change was to introduce chamfers to the inside corners of the lip, decreasing the stress concentration factor and increasing the factor of safety to 2.1, again this change taken in isolation. Aggregating these changes increased the overall factor of safety to 3.1 beyond the determined 2.5 minimum. No physical prototype had been created, so testing could only be done in simulations.